All right, talking complex numbers today. So complex numbers, what happens with those is we get the introduction of what we call the imaginary number. So everything you've done so far has been what we call a real number, whether it be rational, so a fraction, decimal that repeats a pattern, or ends, an integer, positive, negative, whole numbers, natural numbers, all those, plus your irrational numbers, which are the ones that don't have any kind of pattern and they go on forever, like pi or the square root of 5. Those numbers are all your irrationals. Those all fell under the category of being a real number. So now we're going to look outside of the real number system and we're going to look at what's called an imaginary number. So that imaginary number is a key component to making up your complex numbers. So with our notes today, we're going to do a little bit in the foldable. Have your notebook with you because we're going to hop out for a minute when we get down to multiplying and dividing. Talk about something that you're going to have to write down in the next page of your notebook. And then we'll come back and finish this up. So if you don't have your notebook with you, pause the video, go get it. Come back and keep going. So the imaginary unit. Our imaginary number, which we refer to as I, represents the square root of -1. Because what was happening is many years before us, people were solving quadratic equations and they were solving them to try to figure out real life problems. And the issue became that some of the roots did not fall on the x-axis. Some of the solutions weren't there. They couldn't find them. So there had to be a way to find them because they had these equations that were resulting in these kinds of answers. So there had to be something. There had to be an answer so that they could figure this out. And that is when they discovered the imaginary unit. So that is our imaginary number I, which represents the square root of -1. So if we have here, for example, the square root of -a, this gets broken up into the square root of -1 times the square root of a. Now you will see teachers write this in different ways. I use 2 separate square root signs. You might see teachers that just write it under 1 square root sign. It really doesn't matter. It's the same thing that's happening here. It's all about preference at that point. So what happens is this square root of -1 here, that simplifies into that imaginary number I. A stays under the radical sign. You would then simplify A. If A is a perfect square, you would just end up taking the square root of it. If A is a non-perfect square, you would try to simplify your radical, which is what we will get into a little bit more later. So, little practice with our imaginary number I there. If we have the square root of -13. So as I was saying, that is the square root of -1 times the square root of 13. That is what's happening there. It's your -1 times your 13. That is how we get our -13. So that square root of -1, that simplifies into I. 13 is not a perfect square, so that's going to stay under the radical sign there. And there is no perfect square that goes into that. So it is going to simply stay as a square root of 13. Second one there, square root of -16. Again, that's the square root of -1 times the square root of 16. 16 is a perfect square. That turns into 4. Square root of -1 is I. Now, you don't need to keep writing this step if you recognize that's just going to turn into 4i. You're more than welcome to write just the 4i. 3, that's going to be the square root of -1 and the square root of 81. 81 is a perfect square. So that turns into 9i. Notice I'm not putting plus or minuses in front of there because the square root sign, that radical sign, was already there. And there's nothing in front of it. So that's telling us that they do want the positive version. If they had a negative in front of it, then I would pick -i. But they didn't. So I don't. All right, so square root sign is already there. They just want the positive version. All right, number 4 here, 300. 300 is not a perfect square. However, 100 is a perfect square, and that goes into 300. So I'm going to separate 300 into 100 and then a 3. The square root of 100 is 10. The square root of negative 1 turns into that I. And then we got the radical 3 after it. So 10I, radical 3. So that is where our imaginary root shows up. And we take the square root of a negative number. Now, we can graph imaginary numbers. But before we graph that, we're going to talk a little bit more about the whole complex portion of it. So I'm going to go back up here to my imaginary unit where I have some space. So the whole idea of a complex number is the form A plus BI. So A represents a real number. BI is your imaginary number. And when you put the two of those together, you get the complex number because it's a combination of both a real number combined with an imaginary number. So down here in that second category that we just did, where we practiced simplifying those radicals to find our imaginary number, those were all examples of just the imaginary part. So just that BI portion of it is what we were doing down there. So again, when you combine it with a number out in front, a real number, that's what makes it a complex. So technically speaking, every number is a complex number. It's just if your A is a 0, then all you see is the imaginary like we had down here. All the ones that we've been dealing with until now, your B was 0. So all you had was the real number portion of it, and that's what you were dealing with. So everything really technically can be classified as a complex number. It's just if it's missing any portion of that, that just means that that value is 0. That's why you don't see it. All right, so getting back down to our graphing. So we can graph these on a coordinate plane, although the coordinate plane is slightly different. So if we take a look here, our y is no longer our y. It's known as the imaginary axis. Your x is the real axis. So this is our complex plane, not our normal coordinate plane. This is our complex plane. That's where we can graph our complex numbers. So when we plot them, the number out in front, that is your x. Your imaginary number, that is your y. So here I have a 3 plus a 2y. So that means I'm going to go to the left 3, up 2. And then what we do is we generally connect that with the origin. So it makes like a ray. So we have the ray with an arrow here at the end. So then what happens with that complex plane is we want to figure out the length of our ray that is created by that complex number. We want to know how long that is. When we find out the length of that, that is known as the, oops, I spelled that wrong, magnitude. So we'll just call that length of ray. So the magnitude is the length of the ray. So when we are trying to find the magnitude, if I were to connect my point down to the x-axis, zoom in a little bit better so you can actually see my lines. There we go. So if I were to connect this down to the x-axis, I end up having a right triangle. So in order to calculate the magnitude, what we end up doing is we use the Pythagorean theorem because the length of our ray is the hypotenuse because it ends up making that right triangle with that x-axis. So you take your real number portion, so in this case 3, and you square it. You use just the coefficient on your imaginary. So I'm not going to use the I, I'm just going to use the 2. And then that's going to equal our x squared. So this becomes 9 plus 4, so that's 13 equals x squared. So the square root of 13 is going to be our magnitude, because I would take the square root of both sides here. So it would give me 13. So we graph. First number is your x, second number is your y. If this first number isn't here, that means your x is 0. So you're just going to be right along your y-axis. And vice versa. If this part wasn't here, you would just be on your x-axis on this coordinate plane. All right, let's take a look at the second one. Negative 2 plus I. So that means I'm going to go to the left 2, up 1. And there's the graph of my complex number. I'm going to calculate the magnitude. A squared plus b squared equals x squared. Again, only the coefficient on that I. The coefficient on this I is a 1. That's 4 plus 1, which will give me 5. And then I square root my 5. So my magnitude would be the square root of 5. And again, the magnitude is the length of it. So the length of this ray here is the square root of 5. All right, one more. Go with purple. So 1, negative 4i, that means I'm going to go to the right one, down 4i. And there is my ray. I'm going to find the magnitude of the ray, also known as the distance of the ray. So 1 squared plus negative 4 squared equals x squared. So that's going to be 1 plus 16, so that's going to give me 17, square root it. My magnitude is the square root of 17. So we graph on the complex plane. That first number, your real number, is your x-axis. Your imaginary number is your y-axis. And we connect it with an arrow. All right, moving on with our complex numbers, adding and subtracting. Adding and subtracting your complex numbers, you're going to add the real numbers out in front, and then you're going to add the imaginaries. I acts just like any other variable that you have. So for this first one here, number 8, I'm going to add my real numbers. 7 plus negative 5 gives me 2. 3i plus 5i gives me 8i. And that's my final answer. The imaginary number always comes at the end. Always. Next one, negative 3 plus 8 is going to give me a 5. I plus negative 7i gives me negative 6i. Bam. Done. Here I'm subtracting, so 10 minus 4 gives me a 6. When I subtract negative I, that means I'm really going to add it, so 3i plus 1i gives me 4i. And then negative 4 minus 5 gives me negative 9. 2i minus 6i gives me negative 8i. So you add the numbers in front, and then you combine your imaginary numbers. All right, so now here's where we're going to hop and pause for a second. When we get into our multiplying and our dividing, which is our last two sections here, we're going to have to be able to simplify your i's. So before you can simplify i's, we need to talk about the powers of I. Now, it's not a superhero. You can't stop time. You can't make itself disappear. But the powers of I have to deal with the exponent. So, the powers of I follow a pattern. So, I to the 0, just like anything else to the 0 power, I to the 0 equals a 1. Again, it follows pretty much all the same rules as everything else, so equals 1. I to the first, not a trick question, is just simply I. I squared means that you would be doing the square root of negative 1, because that's what I represents. Write yourself a little note up here if you need to remember. I is the square root of negative 1. So if I'm doing I squared, that means I'm doing the square root of negative 1 squared. And that square root and that square just cancel each other out. So I squared simplifies down to -1. So then I to the third means you're doing I times I squared, because I would add those exponents. So 1 plus 2 would give me I to the third. The other way you could look at it is you're doing the square root of -1 times the square root of -1 times the square root of -1. Whichever way you want to slice it up, it's the same thing. If I multiply these two, I get -1 times the square root of -1. So this ends up equaling -I. And then the pattern repeats. I to the fourth is the same as I to the 0. I to the fifth is the same as I to the sixth is the same as I squared. And I to the seventh is the same as I cubed. And then it repeats the pattern again. So I to the 8th is 1. I to the 9th is I to the 10th is -1. I to the 11th is -I. And then it repeats it again. So it just keeps repeating this pattern over and over and over again. So when you're dealing with your imaginary numbers, you should never have an exponent higher than a 1 on there. If it does have an exponent higher than a 1, you need to simplify it. So there is a way to be able to easily simplify it without having to keep following the pattern and keep counting and being like, okay, well, I know the next one, I to the 16th is 1. Like, you don't need to keep writing this chart. There is a simpler way to be able to do it. I like to make a little clock. 1, I, -1, -I. Because that's our pattern. 1, I, -1, -I. 1, I, -1, -I. No. All right. So again, we have a pattern of 4 here. It just keeps repeating one of 4 answers. 1, I, -1, -I. 1, I, -1, -I. 1, I, -1, -I. So let's say I'm trying to figure out I to the 37th power. Again, you don't want to be sitting here going through this list until you get to 37. It's not going to be fun, because especially if I make that like 137, it's not going to be fun. So what we want to do is we want to take your exponent and divide it by 4. We divide by 4 because we have the pattern of those 4 numbers that it simplifies into. 1, I, -1, -I. So that's why we divide by 4, because our pattern is a 4. So when I divide that by 4, I get 9.25. So here's what that means. It's going to complete 9 full circles or cycles, whichever way you want to call it, circles or cycles. So that means it starts up here at the top, because our clock always starts at the top. That's where 12 o'clock is. And it's going to go around 1, 2, 3, 4, 5, 6, 7, 8, 9 full times. So I'm still up here. 9 full times. And then this has 0.25, and that's where it ends. It does a quarter circle. So if I'm up here at 1, my quarter circle is going to put me down at I. So I to the 37th reduces to simply I. And that works with any exponent. So let's say we're trying I to the 26th. Okay, so I'm going to divide 26 divided by 4. That's going to give me 6.5. I don't really care that it makes 6 full cycles around my clock here. I really don't. I could draw it. You could draw it. Go for it. I'm not going to, though. So I know it's going to go 6 full cycles, and then it's going to go a half. So halfway through would be -1. So that's going to simplify to give me -1. Let's try another one. Let's try I to the 44. So if I do 44 divided by 4, I get 11. There's no decimal there. So that means it just does 11 full cycles, and then it's done. So that simplifies to a 1. How about I to the 59th? All right, 59 divided by 4 is going to give us 1. 4 goes into 16 4 times 0.75. So that's going to go around 14 full times, and then 3/4 of a way. So that's going to make that negative I. So when reducing your powers of I, divide that exponent by 4, and that tells you where that number is going to land on your little I clock, as I like to call it. Powers of I. They always reduce to one of those 4 numbers, always. And just like with everything else, we have to always reduce whenever possible. So, going back to here, finishing up our multiplying and dividing. So 5i times 3i, what we're going to do is you're going to multiply your coefficients. So 5 times 3. Multiplying your i's, again, they follow the same rules as any variable. So I times I is going to be I squared. So then looking at my powers of I, because you're going to want to keep looking at that to help refresh your memory, I squared simplifies to be a -1. So I'm doing 15 times -1. So I'm going to get -15 as my answer here. Same thing applies if you have to distribute. So I'm going to do 4i times -3. That's going to give me a -12i. 4i times 2i is going to give me an 8i squared. I squared, I will tell you, is going to be the most common one that you see. So you'll probably memorize that one first. I squared again is -1. So that makes this turn into -8. You'd end up doing 8 times that -1, making it -8. However, this isn't my answer because we can't leave that 12i in front of the 8. You cannot have the imaginary unit first. So we're going to make that -8 minus 12i. And our last one, distributive property, some more. So 2 times 4, 2 times -5i. 7i times 4, 7i times -5i. Bam. All right, so combining my like terms here. First off, I squared again, that's -1 times this -35 makes that really a positive 35. So 35 plus 8 gives me 43. -10i plus 28 gives me a plus 18i. So 43 plus 18i is my final answer for that one. All right. And then division. Our rules with division is that you cannot have an I in the denominator. Reason being, because again, I equals the square root of -1. We're not allowed to have a radical in the denominator, which I know we haven't talked about too much yet, but you can't. It's just not allowed. I don't really know why. It's just not allowed. So what we need to do is we need to rationalize the denominator. Radicals are not rational. Well, radicals of -1 are not rational, so we need to rationalize it. We can't leave it irrational down there. We have to fix it. So if you have just one term down there, in which case I do, I have just 2i, I'm going to multiply the top and bottom by 2i. Reason we're allowed to do this is because 2i over 2i is a 1. So it's like I'm multiplying my fraction times 1. I'm not really changing it. I'm just manipulating it so that I no longer have that imaginary number I in the denominator. So 8 times 2i gives me 16i. 10i times 2i gives me 20i squared. 2i times 2i gives me 4i squared. So again, we just have to clean this up. I squared simplifies to a -1. That's going to give me negative 20 plus 16i, because it's really 20 times negative 1, making it negative 20. And I change the order because, again, that imaginary number always goes at the end. 4 times negative 1 gives me a negative 4 in my denominator now, which is good. Now my denominator is rational. Doesn't have that imaginary number. But I can still go one step further. I can actually divide these. So 20 divided by 4 gives me 5. 16 divided by 4 gives me that negative 4. And that's going to be my final answer there. And then for our last one over here, when we are dividing, this time by a binomial. So monomial, you just multiply times whatever that monomial is. Binomial, you have to multiply by what's called the conjugate. Conjugate is kind of like the inverse. The conjugate of this, you just change your sign to plus. So 2 minus 3i and 2 plus 3i are conjugates. Reason being, when I get my answers, if you remember, when we take the square root of things, we get plus minus. So like, let's say, for example, I have x squared equals 4, square root it, and I actually get plus or minus 2. Those are technically conjugates. If I were to have left this like that, x squared minus 4 instead of square rooting here, and I factored, these are conjugates. They're kind of like inverses of each other. They're virtually the same, it's just one's plus, one's minus. Conjugates exist with imaginary numbers, and we use them a lot with imaginary numbers because they're best friends. This can't go anywhere without that one because that's what creates the quadratic x squared minus 4. They're best friends, they're connected. Very much so the same thing here. You can't have the negative imaginary version without having the positive imaginary version. They're best friends. So, multiplying my top, I get 12 plus 18i. Distributing out my denominator, 2 times 2 gives me 4, 2 times 3i gives me 6i, negative 3i times 2 gives me negative 6i, negative 3i times 3i, negative 9i squared. So now I need to just reduce that. Negative 9 times negative 1, that's going to make this a plus 9. My 6i's are going to cancel each other out. 4 plus 9 gives me 13 in my denominator. My numerator didn't change. 12 plus 18i. It's still 12 plus 18i. And that is our final answer for that one. So, if you have a binomial, switch the sign in the middle. That's known as the conjugate. You multiply top and bottom by that conjugate. Because again, anything over itself is a 1. So really, I'm just multiplying my fraction here times 1. We are manipulating it to get that imaginary number out of the denominator because we can't have it.